There is this very specific, very modern type of heartbreak that I think anyone who has ever played around with AI image generation has absolutely experienced.
Oh, yeah. The almost perfect generation.
Yes, exactly. You
Yeah.
type in your prompt, right?
Mm.
And you wait those agonizing, like, 10 or 15 seconds while the progress bar kind of stutters across the screen,
Mm.
and then boom, it appears.
And it looks incredible at first glance.
It's the absolute perfect image. The lighting is, incredibly cinematic. The composition is flawless. The emotional vibe is exactly what you had in your head. But then,
When you look closer.
right, you lean in, you look a little closer, and you realize there's one tiny infuriating mistake.
Mm.
Like maybe you generated this beautiful, complex infographic for a big presentation, but right in the center, there is a glaring typo in the main header.
Or you have a stunning architectural render of a living room, but there's a coffee cup just, floating an inch above the coffee table.
Just completely defying all laws of physics.
Yeah.
So you do what feels logical, right? You go back to the prompt box and you politely ask the AI to fix it.
Which is always a mistake.
It really is. You type, like, just fix the typo in the header or remove the floating cup. You hit generate and, well, the AI completely destroys the image.
It gives you an entirely different living room. The lighting is gone. The furniture has changed. The angle is completely different.
The magic is just gone. It's like you asked a master oil painter to fix a tiny smudge in the corner of a landscape, and their response was to just set the canvas on fire, throw the easel out the window, and start painting a completely different mountain range.
It is maddening. I mean, it really is.
It's so frustrating. And that frustration, that feeling of having zero control over the final mile of your creation is exactly why we are here today. So welcome to today's deep dive. We are thrilled to have you listening. Our mission for this session, for you, is to give you a highly structured, incredibly comprehensive overview of how to solve this exact problem. And we're going to do it using something called JSON.
And listen, if you just heard the acronym JSON and felt your blood pressure spike because you have absolutely no coding background,
Please do not panic.
right? Do not panic. We are going to completely demystify this. We're looking at a fascinating stack of notes and research dated March 30, 2026.
Yeah, and this research details the exact capabilities of Google Gemini's Nano Banana models.
The overarching goal here is to transition you from feeling like you are, pulling the lever on a slot machine to feeling like you are operating precision machinery.
Which sounds great.
It is. And you do not need a degree in computer science to do this. You just need to understand how the machine categorizes information.
So just to give you a roadmap of where we are heading today, we're going to start by defining the vocabulary so you actually know what the machine is thinking. Then we are going to unpack the core mechanics of how this all works.
And from there, we'll walk through 5 specific real-world workflows.
Right. We're going to start with basic surgical text fixes, scale up to translating complex layouts, swap out 3D objects, tackle the total nightmare of resizing images, and finally,
The best part?
yeah, the really cool stuff, we are going to look at advanced photography style cloning, like literally stealing the mathematical aesthetic of $1 million studio shoot.
And finally, we'll give you some exercises to try on your own and, look at where the bleeding edge of this tech is heading.
It is a dense stack of research, but the practical applications are going to change how you work with digital assets entirely.
Oh, completely.
So let's unpack the core problem. If traditional text prompting is like wrestling smoke because it's unpredictable, it shifts, it never quite holds the shape you want, then what we are exploring today is finding the exact mathematical recipe to lock your images into place.
Right. But to understand how we stop the AI from hallucinating a whole new image every time we ask for a minor tweak, we first have to understand the language it actually speaks.
When it's not trying to interpret our vague conversational English, right?
Exactly. And that brings us to the foundation of the research. We have to define what JSON actually is in this context. The acronym stands for JavaScript Object Notation.
Which immediately sounds terrifying to non-coders.
It does. Historically, the moment people hear that, they picture like a software engineer in a dark room scrolling through thousands of lines of glowing green code.
Matrix style.
Matrix style, yeah. But in the world of modern AI image generation, JSON isn't code in the sense of a program that runs or executes. It is simply a highly organized text format for storing data.
Okay, so just text.
Just text. Think of it as a meticulously labeled, incredibly rigid filing cabinet for every single pixel, every shadow, every texture, and every visual element in a given image.
So instead of a descriptive paragraph like, a moody room with a blue wall and bright light coming from the left, which leaves a lot of room for interpretation.
Right, the AI has to guess what moody means.
Exactly.
Mm.
But the JSON format breaks it down into a strict list instead.
Precisely. It strips away the subjective nature of language. Inside this text file, you have what are called key value pairs.
Key value pairs.
Yeah, so you have a key, like wall color, and a value, like the exact hexadecimal code #000FF for pure blue.
Huh.
You have a key for light source direction and a value of 45 degrees northwest. It is pure structured data. There is no ambiguity.
Which means it removes the AI's ability to guess.
Yes.
And that guessing is the root cause of the heartbreak we talked about at the top of the show, right? The research actually has a formal name for that phenomenon, doesn't it?
It does. The notes refer to it as regeneration roulette.
Regeneration roulette, that is so accurate.
It's that frustrating slot machine experience where the AI completely rebuilds an image from scratch. And the reason regeneration roulette happens is because natural language prompts inherently force the AI to process your request creatively from random noise every single time.
Because when I type, fix the coffee cup, the AI doesn't actually know I want to keep the old image. It just sees a new text prompt and starts the diffusion process. The literal generation of an image from static all over again.
It treats every single prompt as a blank canvas. It has no structural memory of the previous generation unless you explicitly provide it in a language it fundamentally respects.
Which leads us to the antidote to regeneration roulette, which the notes call deterministic technical control.
Right. When you hand the AI a JSON file, you are providing it with deterministic control. This means the AI is instructed to treat that labeled filing cabinet as absolute technical law.
Okay.
It ceases to be a creative collaborator interpreting a vibe, and it becomes a rigid contractor following a blueprint. It says, do not guess the lighting. Look at line 42. The lighting is mathematically locked right here.
And the mechanism that makes this deterministic control actually function is a concept called attribute isolation.
Yes, attribute isolation. This is the massive paradigm shift that makes the JSON method so powerful. Well, because the data is organized into those neat, distinct labeled categories, those file folders, it allows the user to isolate and change a single variable without triggering a cascade of changes across the rest of the image.
Oh, I see. So if I open the JSON folder labeled wall color, change the hex code from blue to red, and close the folder, the AI knows that the folder labeled lighting vectors or the folder labeled furniture layout were completely untouched.
Exactly. It recalculates only the specific pixels affected by the variable you altered, leaving the rest of the mathematical structure intact.
Okay, let's pause and look under the hood for a second, because, if JSON is ultimately just text, just English words, brackets, and numbers typed out in a document, how is the AI actually understanding it differently than when I just type a very detailed bulleted text prompt?
That's a great question.
Because I could type, wall color, red lighting, 45 degrees into the regular prompt box, and it would still probably give me regeneration roulette. Why does the AI suddenly respect the filing cabinet when it ignores my heavily structured paragraphs?
That touches on the core architectural difference of the model the research focuses on. The notes highlight that Google Gemini achieves this using a specific model architecture called Nano Banana 2.
Nano Banana 2.
Yeah. This is critical. Nano Banana 2 isn't just a standard text-to-image model that we've taught a clever new trick. It is the first major image model that has been natively optimized from the ground up to read and parse this type of structured data.
So it's fundamentally wired differently than older models.
Vastly different. Standard AI models are trained primarily on billions of images paired with their natural language captions. They learn loose associations.
Right.
They learn what moody generally looks like or what cyberpunk generally entails. But Nano Banana 2 has a specialized parsing engine.
Okay.
It has been trained to look at a fully rendered image, reverse engineer the underlying math of the spatial coordinates, the volumetric density, and the color values, and output that math strictly as JSON. And conversely, it can ingest a raw JSON file and render the image. It is literally built to read the filing cabinet natively. It bypasses the natural language interpretation layer entirely when you feed it structured data.
It's speaking its native mathematical tongue. Whereas before, we were always forcing it to translate our messy human language into its native math behind the scenes, and things were getting lost in translation.
That is a highly accurate way to visualize it. You are cutting out the middleman of language interpretation.
So we know the vocabulary now. We know we want deterministic control to avoid regeneration roulette, and we achieve that through attribute isolation.
Right.
But that brings up the obvious operational question. How do we actually get this map, this JSON code, out of an image in the first place? If I have an image I generated yesterday, how do I extract the filing cabinet?
The sources outline two core concepts for the operational phase. The first concept is the extraction of what the research refers to as the image DNA.
Image DNA. It sounds very clinical, but it perfectly describes what we were looking for.
The image DNA is all that underlying technical data we've been discussing. And to extract it, you do not need complex programming environments or third-party developer tools.
Thank goodness.
You use a specific natural language command within the Gemini interface, which the notes call a master prompt.
A master prompt. Okay, what is it?
If you have an image you want to manipulate, you upload it to Gemini, making sure you have selected the Nano Banana 2 model from the dropdown, and you type a highly specific directive. Extract all the information from this image and convert it into structured JSON.
That's the entire extraction process. You literally just ask the model to dump its internal data structure.
That is the master key. When you execute that prompt, Nano Banana 2 analyzes the pixel grid, runs its reverse engineering protocols, and outputs a clean, raw text block.
And what does that text block actually look like to the human eye? Because if we are demystifying this for non-coders, we need to know what we are staring at when the AI spits this out.
It will look intimidating for about 5 seconds. It will be enclosed in curly brackets. You'll see a lot of quotation marks and colons. But once you look past the punctuation, it is incredibly readable.
Like just English words.
Yes, you will see clear English labels. You'll see a line that says, object 1, leather sofa. Below that, you'll see spatial coordinates, followed by X and Y axis numbers indicating exactly where on the canvas the sofa sits.
Oh, wow.
You'll see hex color, #8B4512. You will see lighting environment detailing the ambient light intensity and the directional shadows. You have successfully pulled the technical DNA of the image out into an editable format.
Okay, so I have this block of text. I have the blueprint. I scroll through it. I find the typo in the text block, or I find the hex code for the wall color, and I backspace and type in my new value. Now what? Do I just copy that entire block of text, paste it back into the empty prompt box, and hit enter?
No, and if you do that, you will fail.
Good to know.
This brings us to the second, and arguably the most structurally critical concept in this entire research document, the structural anchor.
The structural anchor. Let's break that down, because the notes emphasize this heavily.
If you take your newly edited JSON code and feed it back to the AI entirely by itself, the model will read the math and attempt to build an image from it. But because AI generation fundamentally involves latent noise.
Which is like a sort of calculated randomness used to build textures and find details, right?
Exactly. Because of that noise, the new image might still drift slightly from your original. The leather on the sofa might have a different grain. The lighting might be mathematically correct according to the JSON, but visually slightly different.
Okay, I see.
The JSON is a blueprint, but a blueprint isn't the building. To guarantee a 100% attribute isolation, you must re-upload the original unedited image alongside your newly edited JSON code. The original image serves as the structural anchor.
Let me see if I can visualize the mechanics of this. So the original image is like a physical house that's already been built and is sitting on a lot. And the JSON we extracted is the architectural blueprint for that specific house.
I like this analogy, yes.
If I want to change a window on the second floor, I don't just hand a contractor a newly drawn blueprint with the new window and say, build this. If I do, they might drive to an empty lot and build a completely new house.
Right.
It will have a new window, sure, but the brickwork might be slightly different. The landscaping will be new. It's a new build.
And you've lost the specific charm of the original house.
Exactly. So instead, the structural anchor method means I physically take the contractor to the existing house. I stand them in the front yard. I hand them the updated blueprint. And I say, look at this physical house. Look at this new blueprint. Update this specific physical structure to match the new mathematical drawing.
That is an exceptionally precise way to understand the mechanism. By providing both the original image, the anchor, and the edited blueprint, you are forcing the AI's rendering engine to map the new mathematical instructions directly onto the existing pixel grid.
So it's doing a direct comparison.
Yes. The AI looks at the JSON, sees that you changed the window variable, it looks at the original image, sees the old window, and it recalculates only the pixels within those specific spatial coordinates.
Oh, that's brilliant.
Because you didn't change the variables for the brickwork or the landscaping in the JSON, and the original image already has those elements perfectly rendered, the AI leaves those pixels 100% identical. It is a mathematical surgical strike.
It's forcing the model to run a differential analysis. It compares the old image to the new math,
Yeah.
finds the delta, and only renders the delta. Okay, so with that deep mechanical foundation laid, we understand JSON syntax, we know how to extract the DNA, and we understand the absolute necessity of the structural anchor. Let's move from theory into actual day-to-day practice.
Let's do it.
Let's examine the workflows the sources outlined, starting with the absolute most common baseline headache we all face: text generation and typos.
This is where the return on investment for learning this method becomes immediately apparent. Workflow 1 in the research focuses on surgical text correction.
Let's set a really specific scene here. Say you work at an ad agency, or you are a solo consultant. You've used Gemini to generate a stunning 4K resolution infographic for a biomedical conference.
Okay.
It is a masterpiece. It has translucent 3D charts, glowing icons. The color palette is a flawless, sophisticated corporate blue and silver. It has a subtle gradient background that perfectly ties it all together. You're ready to present it. But then
Find the typo.
you zoom in on the main, massive header text, and instead of saying translunar injection, the AI hallucinated during the generation process and wrote translunar inaction.
It's nonsensical, and in the traditional graphic design pipeline, fixing that text in an AI-generated image is a nightmare.
It's hours of work. You have to take the image into Photoshop. You have to carefully use the clone stamp or content-aware fill to paint out the bad text, which usually destroys that beautiful, subtle background gradient.
Always.
Then you have to guess the exact proprietary font the AI invented, try to match the kerning, the spacing, the 15-degree drop shadow the AI applied. It never looks quite right. It always looks patched.
But using the JSON blueprint method, that hours-long Photoshop nightmare becomes a 3-minute technical adjustment.
Walk me through it.
You follow the extraction concept, you upload the flawed infographic to Nano Banana 2, and you use the master prompt. Extract all visual information, including text content, and format it as a structured JSON file.
Okay.
The model processes the image and spits out the data. Now, you don't even need to read the whole file. You just hit Ctrl plus F or Command plus F and search for the phrase translunar inaction.
It isolates the text that cleanly.
Completely cleanly. It will be nestled within a key value pair. You will see a key labeled text content, and next to it, in quotation marks, is the hallucinated phrase. All you do is place your cursor inside those quotation marks, delete the bad phrase, and type translunar injection.
It is genuinely like editing a Word document.
Yeah.
But I have to ask about the syntax reality here, because we promised to demystify this for non-coders. When I am deleting that text and typing the new words, what happens if I accidentally delete one of those quotation marks, or I accidentally erase the comma at the end of the line? Does the AI just figure it out?
This is a critical technical warning that the research notes highlight, and it's vital for anyone trying this. No, the AI will not figure it out.
It won't.
If you delete a quotation mark, or a comma, or a bracket, you will cause what is known as a fatal parsing error. JSON is strict data. It is not natural language.
Oh.
But the syntax is broken. The AI's parser crashes because it can no longer understand the structure of the filing cabinet. It will reject the prompt entirely. So the golden rule of JSON editing is only ever change the data inside the quotation marks. Never touch the punctuation.
That is a phenomenal piece of practical advice. Respect the punctuation. Okay, so I've carefully changed the words inside the quotes. The syntax is pristine. I take this updated JSON block, I feed it back to Gemini, and crucially, I re-upload the original infographic with the typo to serve as my structural anchor.
Exactly. And your prompt alongside those two elements is simple. Regenerate the image using this newly updated JSON.
And the result?
The AI's rendering engine reads the code, it cross-references it with the anchor image. It sees that out of the thousands of variables in the scene, the only mathematical difference is the string of characters in the text content field.
Okay.
It surgically recalculates only the pixels that make up those letters.
Yeah.
The proprietary font the AI originally invented, it retains it perfectly. The kerning, the 15-degree drop shadow, maintained.
And the gradient.
And most importantly, that subtle, complex background gradient behind the text remains flawlessly untouched because its mathematical coordinates were never altered.
It is the ultimate surgical strike. It fixes the problem without creating 3 new ones. And the sources don't just stop at fixing minor typos. They take this exact same mechanical concept and scale it up to workflow 2, which is automated infographic translation.
If you are working in global marketing or education, this specific workflow is revolutionary.
Because let's stick with our ad agency scenario. You have this perfect biomedical infographic. It's approved. But now the client says, fantastic, we need this localized for our European and Asian markets. We need a Spanish version, a German version, and a Japanese version by tomorrow morning.
Historically, that means handing the flat image file to a team of graphic designers who now have to manually rebuild the entire architecture of the infographic in Illustrator or Canva to accommodate different languages. It is tedious, expensive Canva juggling.
But with JSON, the operational action is identical to fixing a typo, just on a larger scale.
Yep.
You extract the DNA, you find all the text content blocks scattered throughout the JSON code, and you meticulously swap the English text with your translated Spanish text. Being careful with the syntax, you anchor it with the original image, and you regenerate.
And the AI natively renders the new language directly into the original design architecture. No graphic design skills required. You are literally just swapping the data files in the cabinet.
It is incredibly efficient. However,
There's a however.
yeah, and I think I know what it is, because my brain immediately goes to the physical reality of language translation. Languages do not consume the same amount of visual space.
No, they don't.
If I have a crisp, punchy three-word English header, and I translate it into German, it is almost guaranteed to become a massive compound word behemoth that is twice as long. When I feed that massive German string of text into the JSON and regenerate, does the AI mathematically realize the new word is huge and automatically reshape the whole infographic? Does it politely move the 3D charts out of the way to make room for the new text?
It absolutely does not. And you have just identified a critical limitation that is heavily detailed in the research notes. This limitation is defined as structural rigidity.
Structural rigidity. Let's explore the mechanics of that, because that sounds like a hard boundary we need to respect.
Remember when we discussed deterministic technical control? We said the blueprint is absolute technical law. That law is a double-edged sword. When you extract the JSON, you are not just extracting the words, you are extracting a spatial coordinate bounding box for where those words live.
Okay.
The AI locks that box into an XY coordinate grid. The design template you generated does not possess responsive web design logic. It will not automatically resize or reflow its layout to accommodate new volumetric information.
So the box is mathematically locked at, say, 200 pixels wide, but my new German text requires 400 pixels of space to render legibly.
Precisely. If you attempt to cram a significantly longer text string into that structurally rigid bounding box, the AI will try to follow your command, but it will inevitably overflow the boundaries.
Spills out.
The text might squash together into an illegible mess, or worse, it will overlap with your charts and icons, breaking the visual layout entirely. The structural rigidity that protects your background gradient is the exact same rigidity that refuses to make room for more words.
So the blessing is the curse. The takeaway here is that you have to be highly sensitive to character count. If you're translating or even just doing a heavy text rewrite, you have to manually ensure that your new text roughly matches the physical length of the original text. You cannot put a paragraph into a space mathematically designed for a single word.
It requires an editorial mindset before you execute the technical generation.
That is a vital caveat. And this concept of structural rigidity actually provides the perfect conceptual bridge to our next topic. Because if text has to fit into the exact same mathematical bounding box to avoid breaking the image, what happens when we want to swap physical 3D objects in a scene that might possess entirely different volumetric shapes?
That brings us to workflow 3, surgical object swapping. This is where we transition from altering 2D text layers to manipulating 3D elements within a simulated space. And this is where the physics engine inherent in the Nano Banana 2 model truly flexes its muscles.
Let's visualize another scenario. You have generated a photorealistic image of a modern, minimalist home office. There's a sleek wooden desk. There's perfect golden hour sunlight streaming through a window off camera to the right, casting very distinct long shadows across the desk.
Sounds nice.
Sitting in the middle of the desk is a generic silver laptop. It's a great image, but it's a bit sterile. You realize the laptop is boring. You want to swap the laptop for a vintage brass globe to give the room a more sophisticated, well-traveled atmosphere.
Okay.
Now, if we use traditional prompting and just say, change laptop to globe, we trigger regeneration roulette. The golden hour sunlight might change to harsh overhead lighting. The wooden desk might become glass. The entire room is lost.
But we are operating with JSON now. So we extract the DNA of the office scene. Now, the research notes indicate you have two distinct operational paths here. You can do the manual route, scroll through the JSON, find the object identifier labeled laptop, carefully delete it, and type vintage brass globe. Or if you don't want to dig through the code for objects, the notes detail an AI-assisted instruction method that works alongside the anchor.
How does the AI-assisted method work? Do I just talk to it normally again?
You use natural language, but bounded by the JSON framework. You upload the original image as the anchor, you provide the extracted JSON block, and your prompt is highly specific. Generate a new image using the provided JSON data structure, but execute a variable change. Swap the subject object from laptop to vintage brass globe.
So you were basically giving it a command line instruction to execute a find and replace within the blueprint before it renders.
Exactly. It automates the text editing phase.
Okay, so whether I type it manually or use the instruction, the blueprint now says globe instead of laptop. What is the actual mathematical magic that happens when I hit generate? Because we aren't just pasting a 2D clipart sticker of a globe over the laptop.
No, we are engaging the latent space physics simulation. This goes back to attribute isolation. Because the JSON blueprint strictly locks the lighting environment variables, meaning the AI mathematically understands that the sunlight is coming from exactly 45 degrees to the right with a specific intensity, and because it locks the color palette of the room, the new object is generated natively within those locked parameters.
So the model calculates how light would interact with a spherical brass object versus a flat silver object.
Exactly. It uses simulated ray tracing. The globe will catch the golden hour sunlight on its curved metallic surface perfectly, creating appropriate specular highlights. And crucially, it will calculate and cast a new shadow across the wooden desk that matches the exact physical angle and density of the shadow the laptop used to cast, but shaped like a globe. It doesn't look like a cheap Photoshop composite because, mathematically, the globe was rendered in that exact environment.
The AI is essentially calculating the volumetric density and the material properties of the new object on the fly while respecting the locked environment. That is staggering. But keeping our friend's structural rigidity in mind, I have to deduce that there is a breaking point here.
There always is.
If the physics engine is simulating the environment based on the original object's spatial, coordinates what happens if I take that same office scene and I ask the JSON to swap that small silver laptop for a massive full-grown African elephant.
The system will catastrophically fail.
Why? Mechanically, what happens? Won't it just render an elephant on the desk?
The expert sources confirm this exact boundary. The JSON blueprint excels at isolating specific variables, but it is fundamentally bound by the spatial architecture of the original scene. In the JSON, the laptop was assigned a bounding box that takes up, say, 15% of the desk area.
Okay.
When you request an African elephant, the AI attempts to reconcile two conflicting mathematical commands. It tries to adhere to the structural anchor of the original room layout, while simultaneously trying to render an object whose inherent volumetric logic requires 10 times the available space.
It's a spatial collision.
Precisely. The spatial coordinates clash. The model might attempt a compromise and render a bizarre, laptop-sized miniature elephant. Or, more likely, the conflict will shatter the composition entirely, causing the AI to corrupt the image, warp the desk, or ignore the command. You are demanding the blueprint do something physically impossible within its locked parameters.
Which means we are bumping up against the ultimate boundary of the JSON blueprint method. We can change the text inside a defined box. We can swap a 3D object for another object that roughly occupies the same spatial volume. But we are fundamentally bound by the overall architecture of the generated space. Which brings us perfectly to the next logical hurdle. What happens when we actually need to change the fundamental shape, size, and architecture of the entire image itself? That transitions us to workflow 4, image resizing, layouts, and outpainting.
This is a critical juncture in the research notes because it delineates the limitations of standard JSON extraction and introduces the specific, targeted solutions provided by the pro-tier models. The research explicitly addresses the resizing challenge because it is ubiquitous in professional workflows.
It happens every single day in marketing and design. You spend an hour generating a beautiful vertical 9.16 aspect ratio image for a brand's Instagram reel or phone wallpaper. It's perfect. The client loves it. And then they say, this is the hero image for the campaign. Now we need you to make it horizontal, a 16.9 aspect ratio so we can put it on a highway billboard in a website header.
Right. And if you attempt a major layout resize like that using the standard JSON blueprint method we've been using so far, the results are disastrous. The sources state that forcing a vertical blueprint into a horizontal layout causes the underlying mathematical grid to warp and break.
Because the JSON from the vertical image says, the desk is located at these exact XY coordinates. But when you suddenly change the canvas to be twice as wide, those coordinates no longer map to the same relative visual space.
Exactly. You induce coordinate confusion. The AI attempts to stretch the desk and the window from their vertical coordinate logic to fill the new horizontal mathematical space, and it distorts the pixels horribly. It looks like a funhouse mirror.
That's awful.
The sources actually provide a very succinct analogy for this limitation. They state that with JSON editing, you can paint a room, but you cannot move the walls.
The paint a room, but you cannot move the walls. That perfectly encapsulates the structural rigidity. The JSON is the blueprint of the room as it currently exists. You can change the wallpaper, you can swap the sofa, but the dimensions of the room are mathematically locked.
Exactly.
So, if we can't move the walls with our standard JSON toolkit, how do we solve the client's build order request? Are we forced to go back to regeneration roulette?
No. This is where the notes introduce the specific utility of the Nano Banana Pro model. The Pro architecture has built-in, native capabilities designed specifically to bypass the coordinate rigidity of the standard model. When you need to fundamentally move the walls, you abandon the raw JSON text extraction. Instead, you utilize Nano Banana Pro's native formatting and outpainting tools.
Outpainting. Okay, let's dissect that. How does outpainting mechanically solve the coordinate confusion problem? If I have my vertical phone image and I ask the Pro model to make it a 16.9 cinematic widescreen image, how does it do that without just awkwardly cropping the top and bottom off or stretching it like silly putty?
The mechanism of outpainting is entirely different from stretching. When you feed the vertical image into the Pro model and request a 16.9 expansion, the model essentially places your original vertical image in the dead center of a new, wider, blank mathematical grid.
Okay, so it centers it.
It locks the spatial coordinates of your original image exactly as they are. It does not stretch them. Then, it uses its latent space simulation to invent and generate entirely new content to fill the newly created blank space on the left and right sides.
So if my vertical image was a portrait of a person in a room, it doesn't stretch the person. It analyzes the room they are standing in, understands the perspective and lighting, and mathematically generates the rest of the room around them. It paints the walls that weren't there before.
Precisely. It expands the universe of the image while maintaining perfect visual and mathematical consistency with the original center anchor. It creates new coordinates for the new space, rather than forcing old coordinates to bend.
So the strategic takeaway for the listener is tool selection. We use the standard JSON blueprint method, the surgical text edits, the object swaps when we want to stay inside the room and change the furniture. But the second we need to knock down the walls, change the aspect ratio, or build an addition to the house, we have to switch over to Nano Banana Pro's native outpainting architecture.
You are matching the technical tool to the specific structural challenge.
That makes perfect sense. Okay, we have covered an immense amount of ground. We've fixed text. We've navigated the pitfalls of translation and bounding boxes. We've swapped 3D objects using simulated physics. And we've learned how to expand the universe of an image without breaking the math. Now, we're going to look at what the research sources explicitly label as the pinnacle of this technology.
This is the really exciting stuff.
We are moving into the most advanced, high-end application of the JSON blueprint method. Workflow 5, photography style cloning.
This is where the methodology transitions from fixing errors to proactively engineering aesthetic DNA. The sources are definitive. This represents the highest level of deterministic control achievable in the current iteration of the technology. We're talking about the ability to build a unified visual signature.
Let's contextualize why a unified visual signature is the holy grail for creators. If you are building a brand identity, a corporate portfolio, or even just curating a high-end Instagram feed, visual consistency is paramount. You want an audience to look at an image and subconsciously know it belongs to your brand before they even see the logo.
Absolutely.
Traditionally, achieving that meant hiring the exact same expensive commercial photographer, renting the same studio space, using the exact same lighting grids, and applying the same color grading presets in Lightroom over and over again. It is incredibly resource-intensive.
And if you attempt to achieve that consistency using standard AI text prompting, you fail. You can type cinematic studio lighting, moody blue tones 100 times, and the slot machine will give you 100 slightly different interpretations of what that means.
But style cloning using JSON allows you to isolate the mathematical essence of one perfect image and scale it across thousands of generations with zero deviation. How does the extraction process work for this? Is it different from extracting the DNA of an infographic?
The mechanics are the same, but the master prompt is highly specialized. Instead of asking for general visual data, you upload a professional reference photo, let's say a highly dramatic, perfectly lit corporate headshot from a high-end magazine, and you prompt the Nano 2 model with, describe the photography techniques in this image in JSON format.
Describe the photography techniques. By changing that phrase, we are narrowing the AI's parsing engine to focus solely on the aesthetic metadata, ignoring the actual person in the photo.
Oh.
What specific variables does that JSON file actually contain when it spits it out?
It reverse engineers a highly specific, mathematically precise set of photographic variables. We are not talking about loose descriptors like bright or dark. The JSON will contain arrays detailing the precise lighting setup, the exact angle and intensity of the key light, the mathematical value of the ambient occlusion, the subtle fill light reflecting from off-camera bounce boards. It extracts the simulated lens characteristics, mapping the exact depth of field, the focal length, and the bokeh effect. It pulls the entire color palette and post-processing color grade into strict hexadecimal cones.
It is quite literally ripping the proprietary recipe right out of the photographer's camera. Okay, so I now possess a text file containing the exact mathematical DNA of $1 million studio shoot.
Oh.
How do I actually apply that aesthetic to myself?
You return to the structural anchor protocol, but with a specific operational twist. You upload your own photo, a selfie, alongside the JSON code you just extracted from the high-end reference. And your prompt is simply, generate a photo of this person based on the parameters in the following JSON file.
Wait, hold on. I have to deduce the reality of this because it sounds flawless on paper, but the physics seem incredibly messy.
Oh.
If I upload a grainy, poorly lit selfie taken in my kitchen with harsh overhead fluorescent lights, the visual math of my kitchen is going to clash horribly with the math of the $1 million studio rig in the JSON. There is no way the AI just cleanly overrides my bad lighting and maps the new lighting perfectly on the first try, does it?
Your deduction is spot on, and the expert sources validate your skepticism entirely. It is rarely flawless on the first generation. The research notes heavily emphasize that iteration is a mandatory part of this workflow. You are asking the model to perform an immense amount of complex physics calculation. It is not just slapping an Instagram filter over your selfie.
Mechanically, what is it trying to do that makes it so difficult?
It has to perform 3D topography mapping. The AI reads the math in the JSON blueprint detailing how the studio light should behave in a 3D space. Then it has to analyze your flat 2D kitchen selfie and extrapolate a 3D depth map of your face.
Okay, I follow.
It calculates the exact protrusion of your cheekbones, the angle of your nose, the curve of your jawline. Finally, it attempts to recalculate and remap the highlights and shadows from the JSON lighting blueprint onto your specific extrapolated facial topography. If your initial lighting is terrible, it struggles to build an accurate topographic map.
So how do we set the system up for success? How do we reduce the friction of that topography calculation?
The sources outline a specific methodology for this. First, you must provide the AI with richer topographic data. Instead of uploading one flat kitchen selfie, the research suggests uploading 2 or 3 photos of your face taken from slightly different angles.
Giving it more data.
Yes. This provides the model's spatial engine with a much more accurate 3D understanding of your facial structure, drastically improving its ability to realistically drape the new lighting over your features.
You are basically giving it a 3D scan instead of a 2D snapshot.
Exactly. Second, you must expect to run the generation process iteratively. The first time you run it, the AI might nail the lighting perfectly, but the topography map might have glitched, making your pose look unnaturally stiff or robotic.
Like a mannequin.
Right. The second time, the expression might be slightly off. But by the third or fourth iteration, the model usually resolves the topographic conflicts. You lock in the perfect pose, the right expression, and that flawlessly cloned, mathematically precise studio style.
It requires patience, but the return on that time investment is staggering. Once you have that locked-in image, you possess a repeatable, mathematically exact studio setup that you can deploy endlessly. It completely democratizes high-end visual production.
It removes the barrier of physical resources and replaces it with the barrier of technical understanding.
Which is exactly what we are dismantling today. And that reality of needing to iterate, of taking it step by step, naturally transitions us into the final major segment of our deep dive. We want to move from explaining the underlying mechanics to giving you, the listener, the practical frameworks to actually practice this without getting overwhelmed. What specific skill-building exercises do the sources recommend to build intuition for this system?
The notes outline a very specific learning path. The foundational exercise is governed by what they call the one-change rule.
The one-change rule. That sounds like the bedrock principle of deterministic control.
It is the absolute core of the methodology. The sources strongly emphasize that when you are learning to manipulate JSON, you must practice strict step-by-step iteration. The single biggest mistake new users make is extracting a massive JSON block and then trying to change the wall color, swap the laptop for a globe, fix a typo, and alter the lighting vectors, all in a single prompt.
And mechanically, why does that fail? Does the AI just get confused by too many instructions?
It's not confusion, it's an overwhelming of the structural anchor. When you change too many mathematical variables simultaneously, the delta between the original anchor image and the new JSON blueprint becomes too massive.
I see.
The AI's rendering engine can no longer surgically calculate the differences. It loses deterministic control, the attribute isolation shatters, and the system forcefully reverts right back into regeneration roulette. The image fundamentally breaks.
So the one change rule dictates that you isolate a single variable.
Yes. The exercise is to practice making only one surgical change per generation. Extract the JSON, change the typo in the header, regenerate, stop, evaluate the image. Did the font stay the same? Yes. Okay, now take that new corrected image, make it your new anchor, extract its JSON, and change the wall color. Regenerate, stop.
Just keep repeating that.
By isolating variables sequentially, you maintain the structural lock, and more importantly, you build a deep, intuitive understanding of exactly how the model parses specific data points.
You prove to yourself that the filing cabinet works, drawer by drawer, before you try to reorganize the entire office in the dark. That is incredibly sound advice. What is the next exercise to level up?
Exercise 2 is called Surgical Outfit Changes, and it is designed to build directly upon the photography style cloning we just analyzed. Once you have successfully endured the iteration process, cloned a high-end style onto your face, and locked in that perfect professional headshot, you use that final image as your permanent base layer.
Okay.
Then, you practice iterating on the physical attributes while maintaining the environmental math. You extract the JSON of your perfect headshot, re-upload the image as the anchor, and prompt the AI. Add a tailored navy suit and a crisp white shirt to the subject defined in the JSON.
I see the logic here. Because the JSON has locked the complex lighting vectors, the depth of field, and the color grade, you are testing the AI's ability to render new fabric textures and volumetric clothing shapes underneath that locked lighting map.
Precisely. You get to witness attribute isolation functioning in real time. You watch the AI calculate how the navy wool of the suit absorbs the specific lighting, while your facial topography, your identity, and the million-dollar studio atmosphere remain flawlessly, mathematically constant. It's a masterclass in demonstrating what the blueprint actually controls.
That sounds like an incredibly rewarding way to practice. Now, as we look to the horizon, the sources also point toward the bleeding edge of this technology. What are the advanced areas to explore once you have mastered these foundational exercises?
The research identifies two primary vectors for advanced exploration. The first is a practical business application, brand scalability.
Brand scalability.
Right. Once you understand deterministic control, you should actively explore using JSON blueprints to maintain rigid visual consistency across massive, diverse projects. If you are generating 50 illustrations for a children's storybook or a year's worth of marketing assets for a campaign, you don't rely on luck. You build a master JSON blueprint for the brand's aesthetic, and you ensure every single generation is processed through that specific mathematical filter.
You essentially curate and compile your own custom AI aesthetic model without ever having to write code or train an actual neural network. You just carry your master blueprint with you.
Exactly. It scales your creative vision with mechanical precision. And the second area to explore delves into where the actual underlying technology of model interaction is heading next. The research notes reveal a glimpse into a near-future framework referred to as the JSON Whisperer.
The JSON Whisperer. That sounds vaguely mystical, but I'm assuming it's deeply technical. What exactly is that framework?
It is a fundamentally more advanced, more efficient protocol for how we transmit data to the model. Currently, the workflow we've discussed requires you to extract the entire JSON blueprint, thousands of lines of data, edit a single line, and then transmit the entire massive blueprint back to the AI.
Which is a lot of data moving back and forth.
The JSON Whisperer framework abandons that bulky process. It utilizes something called diff patches, specifically referencing an established engineering protocol known as RFC 6902.
Okay, diff patches and RFC 6902. We are deep in the technical weeds now, which is great, But let's translate that mechanism. What does a diff patch actually do fundamentally?
A diff patch is a formalized way of communicating only the mathematical difference, the delta between two files.
Hmm.
Instead of sending the entire labeled filing cabinet back to the AI's parsing engine, you use a script to transmit only the specific file folder you altered.
Oh, I see.
You're essentially sending a microcommand that says, do not read or process the entire document again. Just take this one specific patch and apply it directly to line 42 of your existing memory.
I see. To use an analogy, if the alternator in my car breaks, I don't send the manufacturer the entire 5,000-page engineering schematic of the whole vehicle and ask them to send me a new car. I just isolate the broken variable, look up the part number, and order the specific replacement alternator.
That is a flawless analogy for how diff patches operate. And this protocol is crucial for two massive reasons outlined in the research. First, we have to talk about network latency and API costs. By transmitting only a tiny patch instead of a massive JSON file, the research notes indicate you reduce token usage by a staggering 31%.
Which means the AI doesn't have to waste expensive compute power rereading and reparsing thousands of lines of data it already processed. It just executes the patch. That saves time and money at scale.
Significantly. But the second reason is even more vital for the concept of deterministic control. Sending only a diff patch mathematically guarantees a triplet isolation.
So it doesn't even see the rest of the file.
Exactly. Because you are only transmitting the specific data for the altered text or the swapped object, it is computationally impossible for the AI's rendering engine to accidentally hallucinate a change to the background gradient or the lighting vectors, because those parts of the code were never even fed into the parser during the generation cycle. It removes the potential for human error in handling large JSON files. It is the absolute ultimate surgical strike.
That is incredible. It takes the precision of the JSON method and optimizes it for industrial scale use. So to pull all of this complex theory and mechanics together into a cohesive summary for you, the listener, your homework is clear. Start small. Do not try to build the Taj Mahal on day one. Upload an image. Extract the JSON DNA. Change one single type.
And just see what happens.
Experience the actual magic of seeing the proprietary font and the background gradient remain mathematically locked. Then, step up to swapping one object. Watch how the physics engine calculates the new shadows. Then, when you truly grasp the mechanics, attempt the iteration required to clone a cinematic lighting setup onto your own photo.
It takes practice.
And through every step of that journey, remember the fundamental paradigm shift we established at the very beginning of this deep dive. The AI is no longer your unpredictable creative collaborator. When you use JSON, it is your strict contractor. It is bound by the absolute technical law of your blueprint.
It represents a profound maturation in how humans interact with generative systems. It moves AI from being a highly entertaining, wildly unpredictable slot machine into a precise, dependable, and highly controllable professional instrument.
It really does.
It hands you total deterministic agency over the final mile of your digital assets. You are no longer crossing your fingers and hoping the generation works. You are actively controlling the underlying math.
Total deterministic agency. That is exactly what we have been searching for since these tools were introduced. Well, that brings us to the end of our incredibly dense roadmap. Thank you so much for coming along with us on this deep dive into the underlying math, the structural rigidity, and the physics of AI imagery. We hope we achieved our mission of demystifying this process and giving you the practical mechanical frameworks to stop wrestling with smoke and start building with blueprints.
It has been a genuinely fascinating technical exploration. And as we wrap up, I would like to leave you with one final, slightly provocative thought to consider as you experiment with this.
Lay it on us.
As we step firmly into this new era, an era where we can surgically extract the exact mathematically precise recipe of a master photographer's signature style, perfectly isolating their nuanced lighting vectors, their specific lens characteristics, and their proprietary color grades, and then perfectly apply that aesthetic DNA to any subject using just a few lines of JSON code. At what point does a photography style cease to be a deeply personal artistic hallmark and fundamentally transition into an open source piece of software that anyone can simply download, patch, and wear?
Oh, wow. From an intangible art form to a replicable, open source mathematical algorithm, that is a wild paradigm-shifting thought to end on. Remember, you aren't at the mercy of the slot machine anymore. You hold the recipe. Thanks for diving deep with us today.